Hello. Yep. Let's get started. Yeah. So we are for the next 3 lectures sort of entering the next step in our journey about lossless compression, going beyond IID data. Okay. So we started the course. We talked about very simple prefix codes. We talked about entropy, and then we started. Then we looked at AEP, which provides like a theoretical foundation for compression. And now, after that, like the last 3-4 lectures, we have been talking about specific entropy coders. So let's take a quick tour of those. We talked about Huffman coding. It's very fast. It is the optimal coder when you're doing like a single symbol or you're doing a particular block. And it will achieve entropy when you work with larger blocks. Of course, the complexity increases exponentially. So it's great in many settings, but you run into this complexity limit when you want to really get close to entropy. So that was the first coder we saw. Actually, any questions about the project before we move? Yep. Okay. Then we saw arithmetic coding. This was a different style of algorithm where the entire input was a single block. And we saw that it will achieve entropy efficiently, basically linear time instead of exponential time, as in the case of Huffman coding. And it reads the entire input as a block, getting a very small, like 2 over n overhead over entropy. So it's great. One main issue is that it involves certain division operations. When you actually do arithmetic coding, like if you do it in float domain, you need like floating point multiplications, which are expensive. If you do it as an integer, which is the more common way, you need division operations, which are again expensive. So it is good, but you won't see arithmetic coding being used in like fast compressors. It's still used in a lot of heavy duty type compressors, and we'll look at some examples. One nice property of arithmetic coding, which will be important to us today and next lecture, is that it works with very complex probability models, far beyond anything we have seen until now in this class. And we'll see some examples next lecture. Okay, finally we looked at ANS in the last lecture. There are 2 variants, RANS, TANS. We mostly talked about RANS, but both of them have their own strengths. Again, they achieve entropy efficiently by treating the entire input as a block. TANS doesn't quite achieve entropy, but it gets close. There is a small overhead over arithmetic, so it's not the best compression, but close enough. Both of them are faster than arithmetic coding, with TANS being particularly fast. It almost approaches Huffman coding speeds. And finally, like the algorithm we see in class is always very simplistic, right? It's like a Python pseudocode. People have figured out how to implement ANS in extremely efficient ways on modern CPU architectures. And that is sort of the reason why it's becoming more and more popular today. So there is only so much we can cover in class, but here are some links if you are more interested in these topics about these entropy coders. The paper by Jarek Duda on RANS and TANS. A couple of few blog posts by people who have actually implemented these algorithms. And really like a lot of sort of the good stuff in compression is on this Russian forum for some reason. But all the big people like Jan Kollett, the creator of Z Standard, and Jarek Duda, the creator of ANS, all of them are on that forum, and they comment on all the latest developments on compression. So if you're interested. Okay, and then this is a table we have been seeing a few times in the last few lectures, right? So Huffman coding 1950s, then 1970s, and then very recent ANS. And they have different speed profiles, different compression ratios, and so on, right? So Huffman coding is the fastest but worse compression, right? RANS, arithmetic coding is the slower one, but best compression basically for the complexity. And RANS and TANS are faster than arithmetic coding and better than Huffman coding, so somewhere in the middle. One thing you note here is that RANS has a very fast decoding compared to arithmetic coding. And we'll look at that in a minute. In many applications, decoding time is crucial, and RANS wins out on that quite a bit, and TANS even more. Okay, so last point on these is that all of these entropy coders are used in practice, sometimes because they are the best tool for the job, and many times because people have been using it and it's hard to switch compression formats, so just legacy reasons. But they have their unique properties, and we will keep coming back to these, both in the next few lectures and in lossy compression. Okay, any questions on this sort of whirlwind tour of entropy coders? Right. The main sort of thing we are doing with this entropy coders is start with a probability distribution, known probability distribution. You have data drawn according to that IID probability distribution, and you want to compress it to its entropy. Basically, that's the block diagram vision of this, right? So you have known P, which is IID, and you have like x1 to xn, and you take your entropy coder, and you get like bits, and you want like this number of bits to be roughly equal to n times the entropy of x. Right. So this is sort of all of these entropy coders fit this basic block diagram. Okay, moving on to the quiz, which hopefully we can do very quickly because I wrote down the answers. Okay, so the first two questions were about RNS encoding and decoding. You just needed to follow the formulas as you saw in class, right? So we have some encoding step, we have some decoding step, right? Quick thing I want to note is that see, in the encoding you need to divide by the frequency of the symbol, and divisions are bad. Basically, that's like good to know. Whereas during encoding, you see there is only one division step, but it's division by m, which is usually a power of 2. So division by power of 2 is very, very cheap on a computer because you just shift left by or shift right by something. So that is like the main reason why the decoding is so much faster, right? If we saw in a couple slides ago, the decoding for RNS was almost double the speed of the encoding because the decoding doesn't have this division operation that the encoding has. So we have this formula. Let's just do it. I won't spend too much time. Talk to us later if you didn't get these. Okay. So you are given some alphabet 0, 1, 2, and you have your symbols with these probabilities 3 by 8, 3 by 8, 2 by 8, right? So first thing you would do is you will say that the common denominator of all these is 8. So you will set this capital M equal to 8. And then you will make this table, which is like symbols, their frequencies, so 3, 3, 2, and the cumulative, which is the running sum of these guys, right? And then you would just apply the formula, right? So let me do one of these. So initially the state is 0. So you do like 0 divided by frequency of 2, which is 2, multiply by 8, plus the cumulative of 2, which is 6, plus 0 modulo frequency of 2, so which is 6, right? Anybody had any issues with this question? Let me know, otherwise I will just write the answers for now. Right. You're just supposed to follow this formula, just do the computations. Okay? Right. Let me do the next one just. So 6 divided by frequency of 0 is 3, multiplied by 8 again, plus cumulative of 0, which is 0, plus 6 modulo the frequency of 0, so 3. So 6 modulo 3 is 0. So only the first term survives and you get 16. After you do all of it, you should get 114. Right. Just substitute. Okay. Second one, we asked you to decode. So you were given something where the final state was 117 and you had 4 symbols and you are supposed to now decode it. Again, make the table, right? Yeah. Make the table. And what do we have here? We have, we'll follow the steps which you can see. Yes. Okay. So let's do this. So block ID is 117 divided by M, which is 8, and you take the floor, which if you do it is 14. So block ID will be 14. Slot is 117 modulo 8. So 112 is a multiple of 8. So this will be 5. Then this step, find bin, cumul array slot. So what this means is you make this sort of thing where you mark the different symbols, right? So the frequency of 0 is 3. So this is 3. Then frequency of 1 is 3. So 3. Frequency of 2 is 2. Okay. And then you need to locate 5 in this thing. So because your slot is 5, so 5 is here, right? So this slot was 5, and then S is equal to 1 because this lies in this slot. And then you do this calculation, block ID times frequency plus slot minus cumulative S. So block ID was 14 times frequency of 1, which is 3, plus slot 5 minus cumulative of 1, 3. $44. Okay. Right. Any questions? So one quick thing is again, always focus on the main step, right? So main thing here is this step really. So you are doing, what this is doing really is X next is X multiplied by, or yeah, so you're doing X divided by the probability of X really. And all of this is like doing X multiplied by probability of X. Right, so that is the main operation. That is what gives you the log 1 by px result and so on. Right. So just remember that is the core lesson. Please watch the lecture from last time or do the last question in the homework if you want to learn more about RANS. Okay, here I will ask for your help. So the question is when do you want to use ANS as opposed to Huffman or arithmetic, right? So first part, your application requires the best compression ratio and you are willing to sacrifice encoding or decoding speeds. So what do you think should be the answer here? Is ANS the best answer or something else? Okay, I see some heads shaking. So here actually arithmetic is typically the best answer. Talk to us later if you thought differently. Your application requires extremely fast encoding, decoding, and you are willing to sacrifice. So here the answer is clear, it's Huffman, right? If you look at that table from a few slides ago, you can't beat Huffman at speed. Okay, just so simple. Your application requires adaptive decoding. So we haven't talked as much about this adaptive stuff yet. I think we mentioned it in class. We will talk about it next lecture. Again, talk to us if you were confused. But here really the best answer is arithmetic coding. I think this was in one of the slides last lecture. Okay. But you will understand what we mean by adaptive in the next lecture. Okay. Okay, so the last two, you care about achieving close to optimal compression, but also want good speed. Here, I hope some of you thought ANS was the answer, and yes, indeed it is. And the last one is, you are working with a modern processor, want to exploit parallel processing while still achieving close to optimal compression. So this is this SIMD stuff that I was talking about, single instruction, multiple data. These are special instructions on the modern x86, like the Intel machines, also similar on the ARM machines, where if you're doing the same sort of operation again and again, you can parallelize that operation. And it's very interesting the way they do it with RANS. I will not talk about it too much, but the basic idea is like you have your symbols, right? Symbol 1, symbol 2, symbol so on. What you do is you compress symbol 1, 3, 5, 7 and symbol 2, 4, 6, 8 in parallel basically. Which is like very, very suitable for these modern processors who can do these two operations in parallel basically you get 2x speed up without using 2 cores. You need to write the code in a proper way, but I think there was a paper I linked in the, if you want to read more, this paper. So this paper should give you a sense of that sort of parallel encoding decoding. Okay, so here the last two are the answers. Sometimes these are a bit confusing. The idea is to get you to appreciate sort of the relative importance, relative strengths and weaknesses of all these compressors. So yeah, in this case, the last two. Okay. Okay, any questions so far? We'll now start the material. Yeah.
Just a quick question about the first choice. I actually thought that one was true because if you look at the table of the speeds, T A and S actually has the same optimal compression ratio and significantly higher encoding and decoding speeds compared to arithmetic. That table.
Yes, so if you look at these two.
Compared to T A and S.
Yeah, but even RANS, right? RANS is same compression as arithmetic in this table, and it's just faster at decoding. TANS is slightly overhead, I guess. It depends on the use case. Talk to us. Talk to us, or make a regrade thing, and we will consider. I think the first one I agree might be a bit. It's not as clear. Yeah. Okay, honest advice. If you have IID data and you know it's IID, don't use arithmetic coding. Use RANS or TANS. Simple, right? You don't want to use arithmetic coding for IID data. Really today, the only reason to use arithmetic coding if you have non-IID or adaptive type of data distributions.
Can you start another point? So that table is on a specific data, right? So don't overread the table. That is going to motivate us not for everything out there. As Shubham has been saying, and as we'll learn in the next lectures, the real use case of arithmetic is that it allows you to adaptively work with probabilities, which is sort of the best thing which you can do, no matter what, because of the reasons that we'll learn shortly. Yeah. But
make a regret thing. I think let's not worry too much about. These are small things. I think as long as you understand the concept, that's what matters. Okay. We will move on. But you will see arithmetic coding is much more powerful. We haven't seen the full power yet. Okay, how many of you have seen this, read this novel, or identify the novel? Anyone? Disappointed. Okay, so this is the Hound of Baskerville by Arthur Conan Doyle, Sherlock Holmes, right? So it's a nice book. This is one of the paragraphs. Okay, so we read all these entropy coding and so on, right? So I thought let's try to compress this book, right? And I basically called this get entropy function to get the entropy, the empirical entropy, right? You compute the frequency of each of the letters and you do it. And I got this 199 bytes, 199 kilobytes, where the original file was 387 kilobytes. So that's good. That's roughly a 2x compression. We are happy? No, we are not, because then I tried to compress it with gzip and bzip too, which are some standard compressors. They're not even state of the art. They're pretty old, 20-year-old compressors, 30-year-old now, right? And they get much smaller than entropy, right? But didn't we study that entropy is the best you can do? Entropy is the lower bound on any prefix-free, any lossless compressor. Okay. So, any suggestions? Why is entropy not the best you can do? Actually, some of you might have noticed it in homework 1. I think we had a question where we asked you to do gzip on a file and you saw that it was better than Huffman.
I think it has to do with the fact that each letter, you can look at the probability given the previous letter. For example, if you have the letter T, there's a high probability the next letter is going to be H, for example. So maybe with that you can get better performance.
Yeah. So the very, very good answer, which is that all of this is based on IID assumption, right? For the first 7 lectures, we just studied IID. So there is a risk that we assume the world is just IID, everything is independent of everything else. It is not, we know that. So the example was, if your previous letter is a T, you know with very high probability or with some probability that the next letter might be a T, H, right? You have the, then, this, that, like a lot of words like that. Even stronger example, right? If your previous letter was a Q, you know with even higher probability that the next letter is going to be a U, right? So, or if you're like doing English, right, and you had a start of a sentence, you know that the first letter will be capitalized, and then you have like small letters. You know that. So there are a lot of things you know about English, which are not explained by this IID property. IID would just say that you have 15% E's and 10% T's and so on, right? But it says nothing about like if the previous symbol was something, what is the next symbol? So again, IID means independent and identically distributed, right? So which says that each of your symbols is independent of each other, and they have the same distribution. But what you will see is that given your past, actually the distribution keeps changing from symbol to symbol. So that's the first thing. And there are other reasons, right? Like if you just compute the entropy on you just concatenate 2 files. You take Java code and you take the Sherlock Holmes book and you concatenate them. And you compute the entropy on both of them. The entropy will be like a mix of the 2 entropies. It's not the optimal thing to do for either the Java code or for the Sherlock Holmes file. So for these 2 reasons, but really the first one is what we'll focus on for now. Okay, so we'll look at non-IID data, right? We'll look at real life data now. So we'll look at real life data. We will do 2 things. One is non-IID data, and the other is data whose distribution we don't know a priori. So in homework 1, you already saw an example where you were given a file and you computed the empirical entropy, you encoded it with Huffman coding, you stored the code book, right? So that is one way to do it. There are other ways we will look at where, right, like it's easy to say that I get like 50% zeros and 25% ones and 25% twos, but who has seen a real distribution like that, right? Oftentimes when you start with a data source, it's very complicated and you don't know the distribution often. So, right. And we have been talking just about text, but think of images, right? Like if I'm compressing this image, this slide, right? Like it's very correlated, like the nearby pixels. If the nearby pixel is white, it's more likely to be white. The black guys are all like bunched up together, the black pixels, right? If you have a more like scenery sort of thing, you have sky, the blue colors are like nearby. So there is some correlation nearby, right? If you think of video is also, right, like nearby frames, right? Like even if there is motion, there is a slow motion. So nearby frames look very similar. So again, there is some dependence. Tables and anything in real life, everything is non-IID. Nothing, like very rarely do you get like from nature or from real life a thing that's IID. Okay. Any questions on the motivation part? Right. So, quick outline. Today we will look at for some of you who have done a lot of probability or information theory, today's lecture will be a bit redundant. So please bear with me. Next lecture will be new. Also, if you don't like theory, today's lecture will have a little bit of theory. So again, please. Then lecture 9. So today we will do like basically the equivalent of entropy, but for non-IID distributions. And then we will do next lecture. We will start looking at some more like some practical schemes. For lecture 9 and lecture 10 are mostly about like schemes for achieving the optimal for non-IID data. And really lecture 10 will be like the last lecture of lossless compression, where we will summarize everything we have learned and look at a bunch of case studies, see how to apply lossless compression in practice. One thing is, I guess I said everything is non-IID, but like don't get disheartened. It's not like everything you have done is, useless, right? We will see that all of these tools we have learned are very, very useful in the this case also, right? Also for lossy compression. Okay. How many of you have seen Markov chains in a previous probability course or information theory or any course at all? Okay, a few of you have, some haven't. It's fine. Don't need to know too many properties, but we will need some basics. Okay, which I will cover. Okay. So recall that if you have a block like U1 through UN, in the IID case, the probability of the joint probability of all of these guys is the product of the probabilities. Okay. But in general, if you have done chain rule, you know that you can't just like write it as a product. You need to do this chain rule where it's like PU1 comma U2 is like PU1 multiplied by PU2 given U1, right? That sort of thing. And then you can keep extending this, right? So just the chain rule. If you've forgotten this part of your probability, we can share some material. Okay. So we will just go all in infinite length sequences now. So given some alphabet U, binary maybe or something else, alphabet maybe like English alphabet, you can create a stochastic process. So a stochastic process or a random process is just any sequence of random variables with arbitrary dependence. And it is characterized by basically for every n, you have to describe the probability distribution for that n tuple. Right? So in the IID case, this is very simple. In the IID case, for any n, this thing factorizes. So you write the probability of U1 through UN is just the product of U1, U2, U3, UN, right? But in general, if you don't assume IID, these could have arbitrary distributions. You have just a bunch of like big distribution tables sitting with you. And this is very, very general. And we won't talk about these. You need to, this is way too general to be of much use in theory. But you need to know there is a notion of a random process where it's just a sequence of random variables with arbitrary dependence amongst. Like a random variable might depend on something that's like million before it. Anything can happen. Okay. I will pause for questions after a couple of these. Okay. Then we have stationary stochastic process or a stationary process, which is a stochastic or a random process that is time invariant. So what it means is that whether you are at position 0 in the process or you are at position 100 or position 1000 or million, the probabilities don't change. It's in a stationary state in a way. We'll look at some examples, but if you like define it very precisely, what it says is that for any n and for any L, the probability that U1 through UN is equal to something is the same as the probability that UL plus 1 to UL plus 1 is equal to something. So this is just saying that if you shift your, like, just as an example, right? Like basically we are saying PU1, U2 will have the same distribution as PU100 and U101. So same distribution. Okay, so this is an example of like a stationary process must satisfy this sort of thing where wherever you are in your time series, it will have the same distribution there, same joint distribution. And in particular, like the general definition is fine, but in particular specific properties are that the mean, variance, entropy, all of these do not change with n, right? So what we are saying is like the expectation of U1 will be the same as expectation of U100, for example, or the entropy of U1 will be the same as entropy of U100, or the entropy of U1 comma U3 will be the same as the entropy of U1000 and U1002. So this sort of properties, right? And even these stationary distributions are not like necessarily very simple. They can have arbitrarily time dependence. So in particular, like U1 and U1 billion can be dependent. It's not like they have to be independent. you can have like very far-reaching dependence. Okay. We will keep moving on. We'll look at examples. You never really need to deal with like a fully general stationary process. So we'll get more and more specific as time goes on. Okay. Any questions so far? Okay. So let's say you have IID sequence, which is a sequence of fair IID coin tosses, right? So probability of head is equal to probability of tail is equal to 1/2. Can someone tell me what is this thing? The probability that the first 4 tosses are in sequence HTTH. Yeah, I'm meaning 1/2 to 4, which is correct, right? Because this is IID, right? So this is just like PU1 equal to H multiplied by PU2 equal to T dot, right? Can somebody tell if I put like some L here? So I just shift it. I'm looking farther in the future, maybe P 100 and 100 and 200 and 300 and 4. What is the probability now? It's the same, right? Because again, it's IID, right? And IID means independent and identically distributed. So all of these have the same distribution. They're all independent. Okay. So you can show with some work that IID implies stationary, right? So any IID process, all the processes you have seen so far are all stationary because they are IID. IID is like a very special case of stationary. Now we'll look at a more complex thing, a Markov process. Right. So a Markov process, if you have not seen one, is you can define it in terms of sort of one-step probabilities. So if you know U1, you can define the probability distribution for U2 conditioned on U1, right? And then if you have U3, then you can define U3 given U2. So the real like property here is that UN is independent of UN minus 2 to U1 given UN minus 1. So what this says is that if you know the just previous symbol, if you know UN minus 1, then your future and past are independent. So the only dependence is like at one symbol level, right? So if you know the previous symbol, that's all you need to know. I tell you like the last million symbols, that doesn't matter. Only need to know the last symbol. That is the property of a Markov process. And I think it's easiest explained through this diagram. So we start with U1, which is uniformly drawn from 0, 1, 2. So let's say you sample 0. Let's say U1 is 0. Okay. So once you are at 0, these arrows show like what is the next symbol. So if you are 0, you see an arrow with 0.5 probability going to 1. And you see an arrow with 0.5 probability staying at 0. So that means that if U1 is 0, then U2 can either be 0 or it can be 1 with half of probability. Right? So it's like a one-step process. I wrote it in another way. Maybe this will be easier for some to understand. U1 is again sampled uniformly and Ui plus 1. So the next one is Ui plus Zi mod 3, where Zi is like 0/1. So basically we are saying if you are at 0, you can go to 0 or you can go to 1. If you are at 1, you can go to 1 or you can go to 2. If you are at 2, you can go to 2 or you can go to 0. So mod 3, right? So you round back to this. So this is saying, this is a very simple Markov process where at every step you either go to yourself or you go to 1 plus u, right? And there are various ways to represent it. Don't really need to like worry too much, but maybe you have seen one of these, not the other. So that's why I made all 3. So this just shows this thing as a table where if you are at 0, then the next guy can be 0 or 1 with 0.5 probability. If you are at 1, then the next guy can be like this too. So that's sort of like another representation. It's called a transition matrix. Or you can write it in the form of an equation, which is not always possible. Or you can write it in this graphical manner. We'll mostly make this graphical manner for the rest of the lecture. Okay, so now let me do this math and stop me whenever you don't like it. Can somebody tell me what this rule is called, this step that I just performed? Okay, so this is just called marginalization, like the opposite of this step, right? Where if you add up U1 over all its values, and then you're just left with U2 basically. So that's marginalization. We will have a quiz question, so I hope this example will help you like do that very easily. Okay, now let's do it this way. PU2 equal to 0. This is very simple. Apologies if you already know this, but we'll do it. Okay, can somebody tell what I did in the second step? This is just the chain rule. Right. These are not hard questions. Just want to make sure we are very comfortable with this. Okay. Now let's just write it down and quickly compute it. U1 equal to 1, U2 equal to 0, given U1 equal to 1, U1 equal to 2, U2 equal to 0. Okay, now I'm going to ask for your help. Please help me fill in each of these. So what is U1 equal to 0? Probability that U1 equal to 0. Yeah, it's 1 over 3. Why? Because U1 is given as uniform 0, 1, 2, right? So let me just fill in all 3 of these because we know all 3 of these are 1 over 3. Okay, somebody tell me what is probability U2 equal to 0 given U1 equal to 0. Somebody else. Half. I hear half, which is correct, right? Because it's basically this branch. Right? If you're at 0, then the next one is 0 with probability half. What is probability that U2 equal to 0 given that U1 equal to 1? Yeah, I hear 0, which is again correct. Why? Because if you are at 1, so you are here, then the probability of going to 0 is like 0, right? There is no way you go back to 0. And again, this guy is half. So after you compute all of this, you will get this thing is equal to 1 over 3. Right? So, right. Right. So its quick note is that for a Markov chain, if you can show that like U2 and U1 have same distribution, that is enough to show that it's stationary. So this implies that it's a stationary Markov chain, and you can easily check that it is stationary here because see U1 had a uniform distribution, and if you compute U2 equal to 0, U2 equal to 1, U2 equal to 2, you will again get the uniform distribution. So the distribution didn't change in one step, and then just by induction you can show that it won't change in the next step also, and then you can show that all joint distribution nothing changes, so it's stationary chain. At every step, each of these guys have one third probability of being in that state. Right. If you don't like fully appreciate it, it's fine, but you will have questions in quiz, so just know that this can be done. This I will leave as a homework. You will have a quiz question which is very similar, which is that if you start with probability if you assume that U1 is equal to 0, actually can somebody help me? Is the process still stationary? Can somebody tell me what is the probability that U2 equal to 0? If U1 is 0, U1 is known to be 0 with probability 1. Yeah, here that U2 is 0 is probability half, right? Why? Because U1 you know definitely is at 0, right? So U2 will be back here with probability half. So is this process stationary? It's not, right? Because clearly the probabilities change. Stationary means that the probability stays constant across time steps. Okay. So it's important that when you have a Markov chain, like you start with the correct distribution. If you don't, then it won't be stationary. Yeah, it's like, that's good to know. I think many of you have done probability, so hopefully nothing new here. Okay, this is probably the more interesting question from a compression perspective. So given this sequence, right, that we just made, can somebody suggest me a way to make it into an IID sequence? This is a Markov sequence, it has dependence, right? Can you help me make it into an IID sequence? And maybe I will write it in a way that will be like easier to understand. So you have U1, then you have U1 plus Z1, where plus is like modulo 3, so we won't write that. And then U2 plus Z2, then U3 plus Z3, ... where Zi's are IID Bernoulli half. Okay, so if I write it in this way, can somebody suggest how can I convert this into a IID sequence? This is my U1, this is my U2, U3, U4. Yeah. Yeah, very good. So you just subtract them, right? So you take like U2 minus U1, which is Z1, right? And then U3 minus U2, which is Z2, and so on. You just subtract them, again modulo 3. And when you subtract them, you get these Z1, Z2 guys, which are IID. Because by definition, the way we defined this is like this, right? So even though originally the process looked more complicated, it had dependence. If you just subtract the consecutive ones, it becomes IID. Not always true, it's not always this simple, but oftentimes you will see that you can do simple transformations on your data. You start with a stationary process, maybe you start with a non-stationary process, and you just do some simple tricks, it becomes IID, and then you apply your favorite Huffman coding or ANS or whatever you like, right? And we'll see this again and again, especially in the lossy compression part. So this is like a very simple transform in a way. It's like delta coding or diff coding.